let's practice drawing our field lines for a few different charge configurations. There's actually one more rule you need. So let's start. Let's think about a charge 2q and a charge minus q. And you might start to realize that if the magnitude of the field is the density of lines, then it seems like it depends on how many lines you decide to draw. Seems kind of arbitrary. I could have drawn 4 lines or 8 lines or 200 lines. And there is sort of a rule when you're drawing these, is that the number of lines emanating from a charge is proportional to the charge. Okay? So what that means is if I'm going to try to draw this one, I have to have twice as many lines going from 2q as I have going from minus q, because it has twice as much magnitude of charge. Proportional to the charge magnitude. Okay? So let's say something that's just a unit, or that has a magnitude of q, we're going to put 8 lines on. 1, 2, 3, 4, 5, 6, 7, 8. And then something with 2q, we're going to put 16 lines. Oh my goodness. 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16. All right. So let's see. And then you start hooking them up, and they kind of hook up like this. This one here is going to be right along the axis. That one clearly is just going to connect those two. Okay? And then it kind of bends itself to where this one kind of will connect to that one, and this one will kind of connect to that one. This is kind of approximate, obviously. I'm not, trying to make this exact. And then this one, the next one around, would come to this one. The next one around would come to that one. And then this one would make it all the way around to there. And the next one would hook up to that one. And then that's it, right? So this one goes off forever this way. If we imagine a test charge, it would never come back. This one goes off forever from that way because they're along the line. And the rest of these just kind of go. They would like to make their way over to that negative charge. They never quite get there. Right? This one comes around and around and around and around. So that's a way you can represent these lines. Now it's a little bit more complicated. It's actually in 3D. Right? Really, it would be the number of lines on each charge distributed over 3 dimensions. But this is a good way to approximately do it in 2D. Here's another example we could work on. Say we had 2 negative charges right next to each other. Okay. We could start by giving each of them, say, 8 lines. And I'm going to be sneaky, or give them each of them 4 lines and just do these 4, like that, coming off the surface. So we got to think, what would these do? Well, if a positive test charge were here, it would want to get sucked onto that one. But if you get farther away, it would be sucked onto that one. So it would actually kind of look like that. It's coming in. It's a little closer to this one, so it goes that way. And that one would kind of go that way. This one would kind of do that. This one would kind of do that. Oops. Kind of do something like this. And what you end up with is sort of a hole here. The density of lines, if we were to add more, it would look a little better. You get the idea. You got a lot of field density as you go around, but right here you have none. That's because the electric field is 0 there. Right? If you were to calculate the electric field exactly between 2 equal charges, it would cancel out. So here you've created a region that's sort of devoid of lines. Okay? We can even do something quantitative with lines. Let's think about a charge plus q here, and the field lines around this individual charge. It goes up like this, out like that, out like that, out like that. We can do another one, that's fine, like that. And they're all going out because it's a positive charge. These were all going in, by the way, because it's a negative charge. We could ask ourselves, what is the electric field at some radius out r, right, in some sphere? Because we kind of said, that the field goes as the number of lines per unit area, right? So E is proportional to, we're not writing an equation, is just proportional to the number of lines per area. Okay? Well, what do we say? The number of lines you put is proportional to the charge magnitude. Okay? So in that case, the E field is also proportional to Q. Here I drew 8 lines for Q. Had it been 2Q, I would have drawn 16 lines. So that's proportional to Q. And what is the area of a sphere? It's 4 pi r squared. Okay. So you can see that just this simple idea of field lines has reproduced basically Coulomb's law, that the electric field is proportional to the charge, and it's proportional as 1 over r squared as you move away from a point charge. And that's simply because the lines get lower and lower in density as you move away as 1 over r squared, just like we know the electric field does. That's why this way of using field lines works well for electric fields. Okay? So you're going to see lots of problems where we use lines. Sometimes you'll see problems where we use vectors. You just want to be able to jump back and forth between both. But the key is to remember they're both 3-dimensional.